Session. So the speaker is Alex Grilo. So Alex got his PhD in Paris, and then he was, well, he still is. He tells me he's like a postdoc in CWI, and he's also one of the research fellows in the quantum program. So he's going to tell us about some of his work in cryptography, in particular zero knowledge. So I hope you're going to tell us about what zero knowledge is for everyone. And it's very nice. There's a very nice construction that mixes the use of quantum error correcting code and also uses techniques from complexity theory, circuit Hamiltonian construction that Sandy told us about on Monday. So thanks.
Thanks for having me here. So as Thomas said, okay, it's a talk on cryptography, but actually it's an intersection of cryptography, TCS, and crypto. In quantum. So my idea is to give the basic notions of every part of these three, these three sets of knowledge, and hopefully everyone be bored at least some part of my talk. So let me start by redefining what interactive proof systems are. And everything starts with NP. So NP formalizes the notion of what efficient proof verification means. So here, we have a polynomial time algorithm that's the verifier, and she wants to solve some problem, but the problem is too hard, so she cannot find the solution herself, but she can verify the solution if someone provides her. So in this setting, we assume that there is a prover that's computationally unbounded that provides her, writes down on a paper and sends her some proof. And given the solution, she can solve the problem herself. She can solve the problem. And formally, we say that a language or a promise problem is an NP if for yes instances there is a message that the prover sends to the verifier that makes her accept. And here we can think about a mathematical statement. So a true mathematical statement should have a proof that makes the verifier to accept. And if the statement is false, no matter what the prover sends, the verifier should reject. But then in computer science, we started thinking, okay, why do we have just one interaction between the prover and a verifier? Why can't we make them talk? And then this complexity class called IP was defined, and here we allow the verifier to challenge and to ask questions again to the prover. And here we want that for the true statements, there is some strategy for the prover that makes the verifier accept. Or for false statements, no matter what the prover answers in these multiple rounds, at the end of the protocol, this verifier should reject with high probability. And it was shown that the interaction is very powerful. So this complexity class IP was shown to be equal to P space. That's complexity class that has all the problems that can be solved in polynomial space. And the moral here is that interaction is important. So please ask me questions. But then we can go even further. We can ask, why do we talk just to one prover? Why can't we have multiple provers? So in this setting, we have this, for instance, two provers that they share some common strategy, but after that they cannot communicate. And again, here we want that for true statements, there exists a strategy for the provers that make the verifier accept true statements. And for false statements, no matter what the prover does, what the provers do, then the verifier should reject with high probability at the end. Yeah?
Acceptance is with probability 1 or also with probability 2?
Oh, okay. In the classical case, we can assume without laws of generality that's probability 1. You can always make it 1. But then in crypto, okay, these models are good, but for crypto, we could ask more. And then, NMIP, it was shown to be even more powerful than P-space. It's shown to solve every problem that can be solved in non-deterministic exponential time. So each model is expected to be much more powerful than the previous one. So, and as I said, in crypto, we want more. And one thing that we could ask here is zero knowledge. So we say that this problem is zero knowledge if at the end of the protocol, the verifier learns nothing from the interaction with the prover. So what does that mean? So formally, we can define it as following. We have, in one hand, we have the scenario where the verifier really interacts with the prover. But here we are paranoid. We want the verifier to learn nothing. So you can even think that the verifier is malicious. So the verifier can deviate from her honest actions in order to gain as much as information as she can. And at the end of the protocol, she has some output that's some random variable x. And we say that the protocol is zero knowledge if you can come up with a simulator that's efficient and does not have access to the, cannot communicate with the prover. And this efficient simulator outputs some random, has some output that here I denote this random variable y. And we say that the protocol is zero knowledge if if x is indistinguishable of y. And defining what indistinguishable is might differ, like you can be more picky. So for instance, in perfect zero knowledge, we want that the distribution of these two random variables is exactly the same. If you have statistical zero knowledge, you just ask, for instance, that the distribution of two is statistically closed. And finally, in computational zero knowledge, you just say that any efficient distinguisher cannot know if she's given the samples from the first distribution or from the second distribution. So intuitively, this is saying that whatever the verifier is learning here, she could have figured out herself. Because there is a simulator that has some sort of transcript that's indistinguishable from the original one. And I discovered this week that I think Shafi had, she put money on people trying to prove that these two are the same. So if you want some money, this is an open question that you should.
We didn't put any money.
It's on the web. Okay, at least.
Web? No.
Okay.
Guarantee you.
Okay, so maybe you have money, maybe you won't. I'll try to, for me, the first time I saw what zero knowledge is, it was a bit magical, so it's not clear if this is possible. So I'll try just to give a quick example of how you can achieve zero knowledge. And this will be done by, I'll show this protocol for, the zero knowledge protocol for three coloring. So the verifier wants to know if a given graph is three colorable. It means that if you can put colors on the vertices such that every edge touches two different colors. So let's, and she cannot, okay, assuming P is different of NP, she cannot do it herself. So she asks the help of a prover that is unbounded and can find such a coloring. And one thing that the prover could do is just send the coloring to the verifier, and the verifier checks if the colors are different. And this protocol is complete, meaning that if the graph is three colorable, then the verifier can check it. If it's sound, no matter what coloring the prover gives, the verifier will find two vertices connected by edge with the same color. But it's far from being zero knowledge, right? The verifier is learning this coloring that she could not have cooked out herself. So let's try something else. So the prover has this coloring. So the first thing that he'll do is shuffle the colors. We'll see later why. And then the prover puts these colors on some safes and send the safes to the verifier, but then keep the code secret of how to open each safe. The verifier picks one of the edges uniformly at random and tells the prover, I want you to open the safes containing these two vertices. The prover answers with the codes for the safe, and then the verifier just opens the two safes and see if the colors are different. And in cryptography, safes are what we call bit commitments, but for the rest of this talk, I'll continue with safes, just like with this analogy. And here, again, we have the protocol is complete, because if the prover followed this protocol, then he will always convince the verifier that the graph is indeed three colorable. If the graph is not three colorable, no matter which coloring the prover sends, the verifier should pick one edge that contains two vertices with the same color, with probability 1 over the number of edges. So with no negligible probability, the verifier will catch this cheating prover. And now finally, this protocol is zero knowledge, because the only thing that the verifier is seeing here are two different colors, and more importantly, two different colors like that each one of them picked independently, uniformly at random, because the prover randomized the colors at first place. Finally, why it's computational zero knowledge? Because the verifier could, for instance, try to open all the safes by brute force. She can try to all the possible codes, and if she succeeds doing that, she has the full coloring, and we know that this should not be possible because there's no simulator that can find such a coloring. But we are in the quantum program. Sorry. Let me try to let me give some things that we know in the classical setting. So there is a seminal result of Bredariol et al. That they show that everything that can be proved with two provers, like in this MIP setting, can be also proven in perfect zero knowledge. Secondly, it was shown that everything that can be solved with one prover, but computational zero knowledge, this is equivalent of one prover interact proof systems, if and only if one-A functions exist. But finally, what's more important to cryptography, we know very efficient ways of having zero knowledge protocols for NP. And this is one of the cornerstones of cryptography, and this is a building block for different constructions, and it helps a lot in practice. But now, okay, as I said, we are in the quantum program, so let's quantize everything that we can. And for each version of these interactive proof systems, we can define its quantum version. So for instance, for QMA, we can consider the setting where the prover and the verifier, they're now quantum. And now the prover sends a quantum proof to the verifier, and then she runs this quantum verification algorithm to decide to accept or reject. Or we have QIP, where both the verifier and the provers exchange messages back and forth. And finally, you have QMIP, where these two provers are quantum, and they can share some entangled state, and then they communicate with this quantum verifier in order to make her accept or reject the input. Actually, we don't need to quantize everything. So it was shown in RUV that actually we can assume that the verifier is classical. We don't have any loss of generality if you assume more provers. But then later, like this breakthrough result, actually they show that two provers are sufficient, like G et al.
What does QMA stand for?
Quantum Merlin-Arthur. Because actually, okay, it's not only the generalization of NP. There's this intermediate class called MA, where the verification is randomized. But I won't talk much about it. But it actually is a quantum version of MA. Okay. And we know that assuming quantum in these one-proof interactive proof systems, this does not give any extra power because QIP is equal to space. But this recent breakthrough shows that allowing quantum in two provers is much more powerful than the quantum case. And also for QMA, we expect it to be more powerful than P. And again, here we can consider, okay, can we have quantum interactive proof systems which are also zero knowledge? And so here, again, we are paranoid and we assume that the verifier could be malicious and cheat in order to learn as much as she can. And we assume that at the end of this protocol with this quantum prover, the verifier outputs some quantum state row. And here we say that the protocol is zero knowledge if you can construct some quantum polynomial time simulator that outputs some quantum state sigma. And again, here we say that's zero knowledge if the output of this malicious verifier and the output of the prover, the simulator, are indistinguishable. And again, here we can have these different levels of zero knowledge. So we say that's perfect zero knowledge when these these reducedness matrices are exactly the same. Or statistical zero knowledge when their trace distance is small, or again, computational zero knowledge if no efficient quantum distinguisher can decide which which state is given as input.
Are the inputs here, so these, it seems like there's a difference between this definition if these are allowed to be quantum states as output.
No, the verifier and the simulator, they're all allowed, in this setting, they're allowed to output quantum states.
But I mean, so are the definitions equivalent if you say that these are just classical bit strings?
No, it's not efficient. I think this, you require more with this. Okay, any more questions? So, the first result of quantum, of zero knowledge in the quantum setting was shown by Watchus, because actually at first, we don't even know if classical zero knowledge protocols are safe against quantum adversaries. In the sense that if the verifier was a quantum algorithm, we don't have any way of, a priori, we didn't know how to use the classical techniques to be able to simulate. And this happens because usually when you construct a classical simulator, here's one way of doing it. The simulator does some guess, and then the simulator tries to run some computation, and at the end of this computation, she checks if the guess was correct or not. If the guess was correct, good. But if it was not correct, she can only roll back. She can roll back and start again. She guesses again, does the computation, and check if the guess is correct. So if the probability of guessing correctly is good enough, you don't have to repeat this process too many times, and you have a simulator. But quantumly, a priori, this is not possible because checking if the guess is correct is is a measurement, and this could destroy information. And what Watchus showed here is that there is a way of having a quantum rewinding in the sense that if you do the guess, you try to run your simulation, you measure at the end. If you're fine, if you guess correctly, good. But if you didn't guess correctly, the information is still there and it's efficiently somehow recoverable. And then you can use another process to simulate until you have the right guess. Then a long time passed, and then Broadbent, G, Song, and Watchus, they proposed in 2016 the first zero-knowledge protocol for QMA, where we assume that the prover are efficient, the prover is efficient, if he's given a copy of the quantum witness. Because the idea is that when you want to use zero-knowledge in cryptography, okay, the prover should be proving an NP statement, but you don't want him to find such an NP statement. We usually assume that he's given it, and after that, he's just running polynomial time computation. And here is a property that we didn't know how to do in the quantum setting. So there is this result of Bredariol et al. Is the first one to achieve also this property. But it's somewhat complicated, and it has several rounds, so there is still some room for improvement here.
So when you say efficient prover, you mean you didn't add any power for the zero knowledge?
No, I mean that the prover is given the QMA witness, and after that he runs just polynomial time computation.
Okay, so to be given a QMA witness means that you can do whatever power you need to add in addition to QMA is to get zero knowledge. You don't need additional power.
Exactly.
That's what I was asking.
Yeah. Okay. Yeah. Then last year, with William Slofstra and Henry Wen, we actually showed that MIP star, as in the classical setting, what was shown by Bredariol et al. If you have the MP star protocol, you can assume it's zero knowledge without loss of generality. And in particular, combining this recent result is very beautiful because, okay, at least in my opinion, because it shows that you can prove that a program halts, and the verifier will only know this bit of information. So in this MIP star protocol. So for me, it's a bit surprising that we can achieve such a strong statement in the quantum setting. And what I will try to explain a bit more later is this technical tool that we use here is what we call locally simulatable codes. And I'll explain it a bit more later.
Question.
Yeah.
So here, is it also follows easily from the previous results that QMIP star equals PZK QMI? Sorry, QMIP equals Q PZK QMIP?
Yes, it is, because you can always go from QMIP to MIP star, and MIP star to PZK MIP star.
Right.
And MIP star is strictly included in QMIP, and also the zero knowledge version.
And they're all actually RA, right?
And they're all actually RA, exactly. Oh yeah, here is I have an equality and not a containment. Yeah. And then there were a bunch of results also for zero knowledge for QMA that came more or less together. So first, in a result with broadband, we show a very simple zero knowledge protocol for QMA. And this is in this same type of commit and open as I explained for the 3-coloring case. And okay, we show several. Okay, we have this. We use it, and we also use this idea to show us some variants of this protocol. But then independently, Coladangelo, Vidic, and Zhang, they also showed a QNIZK protocol for QMA. With considering that the prover and the verifier, they have some setup phase. And Bitansky and Shmueli, they also show quantum zero knowledge argument. Oh, sorry, these two are arguments. A quantum zero knowledge argument for QMA with a constant number of rounds and constant completeness soundness gap. And for the rest of my talk, I'll try to explain a bit more the main technical tools that we have here. So the idea is to at least review some concepts that we have already seen like this week and introduce some new ones. And I'll prove that a simple result that QMA is in perfect zero knowledge MIP star. And this should contain all the main ideas for the final. Okay, if I have time, I'll try to explain a bit more about how to put MIP star in perfect zero knowledge MIP star. And now I'll try to go.
Can I just ask a question on the previous slide?
Sorry, sure.
So in your protocol, the third bullet, it's one round?
It's one round. We need at least 4 provers. So if the number of provers that you have here is bigger than 4, then we're fine. Like you keep the number of provers. But if it's smaller than 4, you need 4. So there is this loss of, like you might increase the number of provers, but it's always just one round. Any more questions?
So the difference between the classical cases there, you need two proofs, yeah, and here you need.
Yeah.
Okay.
Yeah. So yeah, so as I said, like the zero knowledge protocol for RE, it actually requires 4 provers. So still there is some gap between like the parameters. So yeah, and like I'll go to the board now.
And just as a look ahead, so you need 4 because of the properties of for hiding or for getting error code or
For soundness actually. Yeah.
I assume.
Okay, yeah, I'll get later, but the idea is that the protocol goes like the provers should share some state, and you want to confirm that the prover shares the state and do measurements on the state as you command. And in order to do that, you have to encode this witness in an error-correcting code and share among them, and they cannot know if, like, what's the question that you're asking. So the for comes from the, as far as we have, the best error-correcting code that we can do the operations that you need. Okay. I'll get to it later.
So in the case that in a classical, you think of tool really just for hiding purposes, right? You have some sort of code. It's not really error correcting code. It's an encryption code that it is able to.
You need it for soundness as well, right? Because.
Soundness is for the MIP, the converting.
Oh, I see. Oh, no. So.
Your knowledge is this is where you need to.
No. Okay. The for that you need then is not for zero knowledge. It's for. It's just for MIP star. Like for this technique for MIP star for putting.
Somehow comes on as a byproduct.
Yeah. Yeah, you can just encode things differently. Like the state that the share is a bit different, and then it comes for free.
That could have been done maybe with 2, but it's for the.
Yeah.
The quantum soundness you need the 4. Okay.
Yeah. So let's give some steps back. So as I said, we have an IP, we have an algorithm that verifies proof. And this can be seen as you have a classical circuit that contains, let's say, AND, OR, and NOT gates. And this circuit receives as input some string, X. And then you want to know what's the output of this classical circuit. So the NP question is, there exists some input to this classical circuit such that the output is 1. And if I do some labeling of this of these wires, I can set all wires to have some value, let's say y something, y. I can label all of these wires, and I consider the string that's the concatenation of all of these bits. And I call this the history string, so you can see this as the history string of your NP computation. So you can think that, like, if you run this circuit how it is, and then put the values that these wires have here, this string has all the information of all steps of the computation of the circuit C. And the the Cook-Levin theorem morally, what we're doing is creating some 3 constraint satisfaction problem. That's first checking if some given string is actually a history string. And secondly, check if the output is 1, right? Because what we want to do is we want to know if there is some input to the circuit that output is 1. So we want also to know that if the last one is equal to 1. So this is my way, and a very simplistic way of seeing the Cook-Levin theorem. And when you go to the quantum setting, this is the same idea that we use, but because of quantum properties, we need to do it differently. So if you have a quantum circuit for QMA, it receives some input psi, and the QMA verification asks if there is some quantum state psi, such that when you run this quantum circuit and you measure the first bit, the first qubit, you have an output 1. Here, we cannot just copy and paste the values of the circuit because of entanglement. So you cannot just have this part and this part all together. So we have to do it in a different way to show how the history of the computation is. And that's what we saw a couple of times in this week. We have the history state of the computation is, instead of putting all side by side, you stack them together. And you do that by doing a superposition over all the snapshots of the computation. So you have the summation of every timestamp and the snapshot of that timestamp. Okay? And that's what we call the history state of the computation. And here, the quantum Cook-Levin theorem reduces QMA verification to Hamiltonians. And this can be seen as quantum version of CSP. And again, we check if the state is a history state. And that the output is 1. Okay, so that's why that's what's going on when like every time that we do, for instance, delegation of quantum computation, we just care about Hamiltonians and check information because we're actually checking this history state and considering its output. Okay, I think we saw it a couple of times, but if you have questions, let me know. So the second topic that I want to talk about is quantum error correcting codes. So should I go from like start slow, or I don't know how basic it should be?
Basic.
Basic. Okay, good. So as in classical computer science, we want to error correcting codes to, not surprisingly, correct codes. And quantumly, and also classically, we will do this by having some map of, let's say, k qubits to n qubits. But let's go simple. Let's just try to encode 1 qubit. And here, we want to, we want to, in order to make this meaningful, we want this mapping to be an isometry. What I mean is that if you have two states, and you have states phi and psi, and then you have the encoding of phi and psi, the inner product of these two is equal to the inner product of the raw states. And in order to be a good encoding, we need an extra property, that the distance of the code.
It's more of a homomorphism because the n-qubit space is much larger.
Isometry. I said it's an isometry. Okay.
Homomorphism.
A homomorphism? Okay. No, I'm fine with that. So we say that the distance of the code is d, and d here to be 2t plus 1. If for every operation f that's at most t qubits of your state, so if you have the encoding of psi, and you do some operation that does not touch n minus t qubits, then it's possible to recover the encoding of psi. Okay, so this is a simplistic way of seeing error correction, like the property of quantum error correcting codes to correct errors. And an example of quantum error correcting codes is the Steen code, for instance. So it maps 1 qubit into 7 qubits. And yeah, and that's it. Yeah. So, okay, now we know these quantum error correcting codes exist, so we know that we can encode quantum data, but we want to do more, right? We want to do not only like store it, but we want to compute on it. So in fault tolerance quantum computation, there are two main ways of computing on encoded data. And the first one, as Ifke introduced yesterday, is by transversal gates. And in a transversal, a gate said to be transversal, so for instance in the 1 to n qubit code, is that if you apply some operation U on every physical bit of your encoded state, then this is actually the same thing as encoding this operation U in the logical state. Okay? So, and these type of operations, they are very good for fault tolerance because they don't spread the error too much, and they are good for fault tolerance. So, for instance, if you're looking into this thin code, we can see that very easily that the NOT operation, X operation, can be done transversally because every bit string in the support of the encoding of 0 is just the negation of a string in the support of the encoding of 1. And actually, we can also show less easily that any Clifford operation can be done transversally when you consider the encoding on the STEAM code.
I think it's longer than that because they're not normalized their states. It probably doesn't matter.
What?
They're not normalized?
Here.
Well, there's 7 cats.
So they're not. No, okay, yeah. No, I think this, okay, I'm missing one. Another. Okay. But it's well known that, for instance, for STEAM codes, you can do Cliffords transversally. But it's well known that no error correcting code can perform universal quantum computation transversally. So we need a different gadget in order to achieve universal fault tolerance quantum computation. And one way of doing that is using what we call magic states. And I'll define by example what I mean by magic states. So in order to do quantum computation, you need Clifford operations plus any non-Clifford gate. So for instance, you can consider the T gate that maps 0 to 0 and 1 to pi over 4 on 1. So it applies this complex phase on when it receives 1 as input. And the T magic state is what you call is this quantum state, and using what has been shown is that using if you provided resources of if you provided copies of these magic states, then you can actually perform the T operation as follows. So you have your state psi on which you want to apply the T gate. You receive one of these magic states T, and then you apply this quantum operation. You apply this operation. So first, you C0. So you apply this C0 here. So this is a Clifford gate that entangles the magic state and your quantum state. Then you measure your original qubit in the computational basis, and then based on this output, you apply a P gate that's also Clifford on the second qubit. And if you do the calculations, you see that the output, if you do everything correctly, then what you're doing here is applying T on your original state psi. And so this computation, what you call computation by teleportation. And here it's useful because, as I said, this is Clifford, and this is also Clifford. And as I said, for instance, for the STEAM code, we know how to do Cliffords transversally. So if you're given the encoding of psi and the encoding of the T gate, then, and you do everything transversally, here you have the encoding of your state applied to the T gate.
Sorry, what is P again?
Oh, P is
H.
1I. But yeah, but this is Clifford. That's the important thing.
Can I ask you, what's the notion of computing on encoded data really? So are you assuming that there's some, someone can corrupt each gate, each wire of the computation?
So
each wire has an encoded...
So okay, for now, I'm just assuming that instead of doing the computation on the raw data, I'm given encoding, and I'm assuming no error. Okay, for the purpose of this talk, I assume no error.
No error.
No error in my case.
Then I could decode the qubits and then compute on them.
Yes, yes. But for now, I'm just introducing the notions. When you're doing actual fault tolerance, what you do is perform gates and then do a correction, perform gates, then do a correction, correct, and continue doing fault tolerance computation.
I think the point is that ultimately these different qubits will be held by different provers, and so if that's your setup, then you cannot decode and compute and re-encode.
So you think about zero knowledge already?
No.
Oh, no, okay.
Just correctness of... so presumably the point here is correctness with noise. And
No. For now, okay, for the purpose of this talk, I want to do the same thing I do without encoding, but with encoding. That's the only thing that I did now.
So I guess the question is why?
Oh, I'll get there. Yeah.
That's what I'm saying. It's important that it's transversal because later, I don't know.
Later, different bits of this encoding, qubits of this encoding will be held by different parties.
Yeah.
That's why I can't decode. Okay.
Yeah.
Okay. Nice.
But even for
That's not really, actually.
Okay.
Yeah.
But
So, okay, but maybe the question is why? Is because quantum error correcting codes are good for secret sharing as well. So, for instance, if you have here the SYN code, you have 7 qubits. And if you do the calculations, if you pick any 2 qubits of the SYN code, they're the totally mixed state. So they have zero information about the encoded state. Okay, so this can be used, for instance, for secret sharing, but the property that we need here is what we call simulatability. So as I said, here, this reduced matrix on 2 qubits is always the totally mixed state. So in particular, there is a very efficient algorithm that's given 2 qubits and outputs what's the reduced density matrix of the state on these 2 qubits. And this algorithm just outputs identity. So it outputs a classical description over these reduced density matrices. And then this inspires us to define what we call these simulatable codes. And one property of these simulatable codes is that there exists this efficient classical algorithm okay, let's assume that this code encodes 1 qubit into n. So it's an n1 quantum error correcting code. And we fix some parameter k, s. And we say that a code is S simulatable if there is efficient classical algorithm that's given a subset of the n qubits, such that the size of the set is at most the parameter S, this simulatability parameter. And it outputs the reduced density matrix of encoding of some qubit psi on S. So let me, okay, after you have this definition, let me go back here. So if you're given a subset, let's say one, like the 5th and the 7th, I want this algorithm to output what's the reduced matrix. So if you forget what we have in the other positions, what the state of the, what's the value, what the state, the reduced state over this encoding. Is it clear what I'm trying to do? I don't think so. Okay. Let me try to explain again. What we're trying to do here is simulate parts of the code. So instead of, we're giving this big error correcting code, and we're just saying, okay, if you look to just 1 or 2 qubits of this big encoding, does it have any information, or can we efficiently compute what's the value that's there? So as I said, for this thin code, if the set has at most 2 qubits, it's fine, but it can be easily seen if you pick 3 of them, then it's not the case anymore. So for instance, if you pick the 3 first qubits, here you have the substring 000, but here you cannot. Yeah.
What's the relation between this S and the distance? Are they?
So yeah, I'll get later for the construction, but S is a function of the distance. So the first question is, can you have, for an arbitrary S, have a simulatable code? And what we show in our result, that yes, you can do, and you do it by just doing iterations. So instead of having one thin code, what you could do, you can do it again and concatenate with itself and compute, for instance, for every qubit of the encoding of your state, you encode it again with this thin code. And for instance, if now you pick 3 qubits here, they're not a totally mixed state, because we see that they cannot be, but they're just the 3 first qubits of the encoding of a totally mixed state. Because we know that this original encoding, if you just look to the first qubit, this is the totally mixed state. So this is a random bit. So these 3 values here is just the encoding of a random bit. And so this reduced decimal matrix can be efficiently computed.
I guess what's confusing me is, are you only asking for a projection, or are you going to simulate some operations?
No, I want you, no. For now, it's just for encoded states.
I see, okay.
But yeah, in a minute I'll address that. Okay? Any more questions? Is it clear what I'm trying to do for now?
Maybe it's mathematically clear, but I don't know why you're doing these things.
Yeah, but yeah, okay, I'll get there. As I actually just asked, okay, we're simulating encoded states, but we want to do computation on quantum states. So for instance, you have the encoding of psi. As I said, if you apply X gates on each of the qubit, at the end I have the encoding of X on psi, because X can be applied transversally. So our definition of simulatability actually asks that if you that you can also simulate every state that's a snapshot of the computation of X transversally. So here we want to simulate the snapshots of the computation. And as you saw, either you can do it transversally, but if you do quickly the calculations, computing the snapshots on transversal computation is the same thing as computing on encoded states, because then trace is cyclic, so you can use these nice properties. But the main obstacle comes when you do magic state gadgets. Because, okay, as you saw here, we know that this magic states gadget can be implemented with Clifford gates and measurements. So the problem here is how can you simulate the measurement that you have here. So hopefully it works because we're lucky. And here the output of this measurement is with probability half 0 and probability half 1. So we know the exact distribution of this outcome. Yeah?
It depends on what your efficiency metric is in. If it's in the number of qubits, but your number of T-gates is constant, then this follows from the Gottesman-Canel theorem. If you want it to be efficient in the number of T-gates, at every T-gate you're going to split in two, and so it's not so efficient anymore.
No. Our argument is independent of the number of T-gates because of the following. Imagine you have a computation that you have some big state psi, and here you do, let's say, a T, and then a Hadamard, then a T, or something like that. But now we're encoding everything, and you're doing the gadgets for every part. So at this stage, everything is encoded. So we know by this property that you can simulate. Then we're doing the T-gate, and then by this property that you can do in the computation, during the computation, this phase of the computation, you can simulate every snapshot, then we are done. Then this part is fine, but then everything here is encoded again.
Okay, as long as S is sufficiently small.
Yeah, you have to tune the parameters. Yes.
Absolutely.
Yeah. So, yeah, having defined the properties, so what we show in this work with William and Harry is that if you pick, let's say, if you fix an S, and then if you concatenate the Stini code by log S plus 3 times, so if you fix some K, then this K concatenation is as simulatable. So the conclusion here is that for any S, for any constant S, there is a constant size error correcting code that's simulatable. And finally, we can, now the idea is that, okay, now I'll put these two ideas together and see why the simulatability is important. So let's go back to our QMA verification. It consists of some state psi, some auxiliary bit 0, and then quantum gates. But when you're doing a QMA verification, you can assume a different circuit. And this circuit is the following. First, instead of assuming psi, it assumes to receive the encoding of psi under some error correcting codes. Then, first you have to check if this encoding is correct, so some error detection here. And you also receive more ancillas, more auxiliary bits. And here, the first thing that the verifier does is first creating magic states and encoding everything. in this step, after doing the error check and creating magic states, and T-gates, everything is encoded. So after that, you can just apply every gate, either by doing it transversally, or using the magic states that we created in this phase. So my claim here is that and at the end of the protocol, of course, you have to output just one bit, so you just decode the first bit and measure it. So my claim here is that by doing this encoded version of the QMA verification protocol, completeness and soundness are exactly the same. Because completeness is trivial, because if psi if encoding of psi is given here, you accept with exactly the same probability as the original verifier, or we would accept with psi. But if you're not given error correcting code, you are a reject. So it can only decrease the probability. And in a more complicated version, what we're showing with Henry and William is that the history state is also simulatable. So if you're given the history state of this encoded computation, when I look to just a few qubits of this proof, you know exactly what the reduced density matrix. Oh, okay, you know with a very good precision what's the reduced density matrix there.
Why did you have to qualify?
Huh?
Why did you have to qualify?
Oh, because QMA does not have perfect completeness. If your QMA verification accepts probability 1, then it's exactly the same.
Do you need an S parameter in that statement? Is it just simulatable or S simulatable?
S simulatable.
And S is going to depend on...
No, S, you fix S, if it's S is a constant as big as you want, and then you pick your correcting code such that it's S simulatable. And then here you pick S qubits, and it's simulatable. Okay?
So S, I should think about it as a constant independent of the size of the history.
Yeah, it's a constant.
The distinguishability of the history state code words is exponentially small?
Yeah. So the point is, the idea is that, this algorithm will output some reduced density matrix that's exponentially close, exponentially small in the reduced matrix of the history state. So we didn't observe this in this paper, but then with broadband, we realized that actually this shows that this what's called the reduced consistency of local reduced density matrix problem. And this problem is as follows.
Do you mean n representability?
We don't prove, this is for fermions, no? Or something like that, no?
No, it does not. It can be bosons too.
Okay, I just know quantum states, I don't know, okay. Okay, if you have a quantum state, but yeah, they're related. Imagine that you're given reduced density matrices. They're supposed to come from this big quantum state, let's say sigma. So you're given, let's say, row 1, row 1, row 2, and so on. So we're given a bunch of reduced density matrices. And the question is there a quantum state that's consistent with all these local parts? And in 2006, this was shown to be in QMA. No, sorry, to be QMA hard. No, it was shown to be in QMA. And QMA is in what we say P to this problem. So it means that if you can solve this problem in unit time, then you can solve QMA. But this is what we call Turing reduction. So what Liu showed is that this problem is QMA hard and there are two reductions. But these are not. This is not the standard type of reductions, and it's not exactly what we want, because for using protocols, you cannot just replace a protocol for CLDM for a protocol for any QMA complete problems, because you have some issues with complement and so on. So what we show with broadband is actually that CLDM is QMA hard. And that's QMA complete. So this is a byproduct of our constructions here. How much time do I have? Minus 5 minutes, okay. Okay. Okay, yeah, I'd like to go back to MIP star, but well, maybe
Show us how these are useful
for zero knowledge, yeah. Okay, or I can, okay, I'll do something simpler. So instead of showing multiple provers, I'll show how this very simple zero knowledge protocol for QMA works. So again here, so you have I'm showing that QMA has a simple ZK protocol.
One prover.
With one prover and computational zero knowledge. So the idea is the following. The prover holds some simulatable witness. So the argument here is that we can assume now that instead of having just the history state, the prover has a encoded history state that's simulatable. Right? This prover puts a one-time pad on this simulatable state to hide it, and commit to these values A and B, and sends everything to the verifier. Okay, so the verifier now holds some encrypted version of the simulatable history state. One thing that I didn't mention is that these checks are all local.
Why is it?
Huh?
You said encoded.
Okay, encrypted because you have a one-time pad now.
In addition, okay.
Okay, just to hide everything. Then the verifier just tell the prover, I want to perform the ith test. And let's say that this ith test just touches S qubits. And then the prover just opens the commitment to the corresponding qubits. So this protocol, okay, my claim is that first, this protocol is complete, because if the prover is, if there exists some state that makes the verifier accept, the prover does everything honestly, and then the verifier accepts with high probability at the end. It is sound, because if this commitment, okay, assuming these commitments are binding, so the prover cannot change his mind of what's inside the safe, then by the soundness of the QMA protocol, the verifier rejects with non-negligible probability. But what we can show is that this protocol is also zero knowledge, because the only thing that the verifier is seeing here is S qubits that are open. That's the only thing that only part of the witness that the verifier is seeing. But this can be simulated by using our simulatable proofs. So so the idea is that the verifier here, since it's one-time padded, it just sees the totemic state, tensors some rho I that he could have computed, she could have computed herself, tensor more identity, let's say, and some commitment to A and B, but since this is hiding, this is not giving any information.
So in your transformation to many provers, you have to just deal with the pad, or you're going to change your encoding?
No, it's how, with multiple provers, instead of measuring them, the verifier is delegating the measurement to the provers. So the provers, okay, the idea is that the provers, you have 4 provers. They share an encoding, so you encode it again, but an outer encoding, and they share this history state, like with an error correcting code. And then the verifier needs to command what measurements to do on a few qubits.
Still, if you want to translate, maybe it's no translation, but you have this pad, yes?
Yeah.
Pad,
Oh, the pad is not, the on-time pad is not needed.
I understand.
Okay, sorry.
One-time pad is what was computational.
Yeah. Yeah.
It's going to be one-time pad, it's going to be
Oh,
computational.
no, sorry, the commitment is computational.
The commitment is computational.
So this is a one-time, if this is a string, this is...
It's the commitment that you need to change.
No, the point is...
You need to remove.
Yes.
Is that where you're adding these other 2 provers, or no?
No.
Okay, so how are you doing that?
So the commitment is just saying, okay, you need provers to be sure that the provers have fixed a quantum state, and whenever you tell them to measure a few qubits, they're still measuring on the same quantum state that they have committed. So the idea is that by not having information, they commit to a state right away, and that's done. Is it clear, more or less? No.
It's not clear. First you said it was computational zero knowledge. Now you're going to go to perfect, right?
I don't know, here's perfect, yeah.
So I'd like to know, where is it that you're removing the computational, and what are you doing in order to get to perfect?
Okay. Here, the computational, so you can always simulate the reduced density matrix. So this part is statistical, or perfect in the right? Computing this is statistical. So if I just reveal a part of the state, I don't have computational assumptions. But here, the prover somehow has to commit to the state, and this commitment to the state is computational.
But you needed the one-time pad because the prover is physically sending the state to the verifier.
Exactly.
Whereas when you have provers, they don't have to send the state to the verifier.
Yeah.
There doesn't need to be a one-time pad, right?
And here, you just command the provers to measure a few qubits of the state. So here, first, yeah, in different ways, you say that measuring a few qubits of the state, they commit the whole state. You do tests for that. But in the honest case, when you're just measuring the qubits, you don't have to see the whole state. You just see the specific part that you know how to simulate. Okay. I hope it is not zero knowledge. And I'd like just to finish with some open questions. And I'm happy to discuss things offline. So first of all, we have been developing better and better zero knowledge protocols in the quantum setting, but the elephant in the room is why? Where can you use it? And classically, classical zero knowledge protocols can be used to construct other primitives. It can be used in a lot of different ways. And quantumly, we still don't know if this is possible or not. Secondly, we know that MIP is equal zero knowledge MIP. We know the MIP star is equal zero knowledge MIP star. Can you go further? So if you give even more power to the provers, that they can share any non-signaling strategy, is zero knowledge making it a smaller class, or or it's still the same? And finally, we're getting better non-interactive zero knowledge for QMA, but none of these approaches, these in the standard CRS models. Okay, can you have more efficient zero knowledge, like more standard non-interactive zero knowledge for QMA? And I think that's all. Thanks.